Okay, so as soon as I get these graded, I will post grades to Canvas. I will post a completed solution set as well to our Canvas page so that you have access to the things I was looking at. And if there are discrepancies, then you can go, hey, wait a minute, and come talk to me about issues that you may see or question between what I've written and what you've done and how they differ. But want to go back to line charts. Because here in the text on page 70, we have two examples of a couple of line charts. The one on the left has two trends. Again, these are time series data. So over time, we're looking at US imports versus exports. And over here, we're looking at the same thing. Why do these two look so different? Well, it has to do with our choice of scale. The x-axes are exactly the same. But over here, we see these numbers jump up by 500 every time. So as I move up from line to line, they're an arithmetic distance apart. We add the same value each bar. In the right picture, those aren't arithmetic. Those are geometric or logarithmic, because we think of them as going up in powers of 10. So I go from 100 to 1,000, I go from 1,000 to 10,000. That tends to smooth out a lot more changes. But it can also make drastic changes appear less so. If you looked at the stock market price over the last 50 years, somebody on the internet right now, Google for me, Dow Jones Industrial Average, 1976. What was the value of the Dow Jones on 1976? Roughly. I want a numerical score. Like it's,
879.
Say again?
879.
So roughly, let's round it to 900. What's the Dow Jones today? $45,000. And if you look, it went from 800 to 1,000 fairly slowly. It went from 1,000 to 10,000 in almost the same length of time as it went from 800 to 1,000. It went from 10,000 to 20,000 in much less time, 20,000 to 30,000 in much less time. As a matter of fact, I think if you go back 10 years, the Dow Jones is below 15,000. It's 45,000 today. That graph looks exponential. It grows really steeply. If I use a logarithmic scale, where instead of actually using the number, I use the logarithm of the number, it'll flatten that into a straight line. And it'll allow me to see the differences a little more carefully. A lot of things that we think of as big scales are actually logarithmic power scales. Sound. Anybody know the unit sounds are measured in?
Is it frequency?
No, that's what tells me what tone I'm getting. The volume of the sound.
Decibels.
Decibels. Bell, after Alexander Graham Bell, is a measure of how much power hits a surface. Each additional bell is a multiplication by a factor of 10. So something at 80 decibels is 10 times louder than something at 70 decibels. The Richter scale. Same thing, it's a logarithmic scale. It's a power of 10. An earthquake at 5.0 is 10 times more powerful than an earthquake at 4.0. If we use the logarithms, we get a more smooth, easier to comprehend graph. pH, acidity, same thing, it's a logarithmic scale. So we use these scales. You should check when you're looking at a chart what am I actually seeing? And how is this data being measured? Because the choice of our axis changes what we see. Questions? One of the more common things we will be doing when looking at data is looking at associations between pieces of data. In which case, instead of using univariate data, I use bivariate data. Here. I want to look at prices versus sales. I want to compare these two together. We're selling bottled water 10 different weeks, same store, we change the price week to week. Well, price changes, units sold. Does price affect sales? How would I know? I have to make a decision before I actually set up the picture I want to draw. I have to decide which I think is the predictor variable, and which I think is the response variable. Do I think that changing price will change sales, or changing sales will change price?
First option.
The first option. I think the price is something that I can control, and I can choose it, and then the number of units sold will be affected by that. So I'm going to take these two pieces of data, and for each of these weeks, I'm going to create an ordered pair. And the thing I think is the cause, although I can't be sure it's a cause, the explanation variable is going to be the x variable, and the response to that is going to be the y variable. So I'm going to write these as x and y, and I'm just going to make a set of ordered pairs. And now I'm going to drag my ass back to algebra class. And I'm going to graph those ordered pairs. Here is my data. I want to create a set of ordered pairs. If I highlight both sets of data, and I go to my recommended charts again, where were recommended charts again?
Another insert and then recommended charts.
So I go to the insert pile on the ribbon. There we are, recommended charts. There we go. That first one, scattered. It looks like a bunch of things scattered on a piece of paper. Okay, what that created for me is a set of XY values. If I hover over one of them, you'll see it actually brings up a little label. And that label says 1.04, 173. And I see that's the third row of my data, isn't it? When my price was $1.04, I sold 173 bottles. So now I can ask, just looking at this picture, is there a relationship here? Can I won't be able to assume anything about cause and effect, but I can say these two things are related to one another, if I believe that to be true. So, in this picture, Leo, you think?
Yeah, like the unit sold depends on my unit price. Like if it's lower, I might be able to sell more than if it's higher, I might not sell as many.
Because it looks like as I go to the right in the x direction, the number of bottles I'm selling is going down. If I lower my price, I'm seeing more. Now, it may very well be that one of these weeks it was incredibly warm. One of these weeks was incredibly cold. There could be other factors, but at least I believe these are related to each other. And so we're going to call this a correlation. Correlation, literally. Correlated data, associations between my two pieces of data, show up best in scatter plots. We can do lots of things here. I want to figure out how to describe what's going on based on my picture. So let's think about what we could see from a scatter plot. In this case, Leo, you said as we lower the price, we're selling more. As we raise the price, we're selling less. Okay. So I'm going to say that if we were to try and group these, maybe put a belt around them, it would look like it was a line that had a negative sort of slope going on. I'm going to say these are negatively correlated. An increase in price brings me a decrease in units sold. So if this goes with a negative correlation, pictures that go with a positive correlation should look like what?
Positive slope.
Ideally, some sort of positive slope. So as I increase whatever my cause variable is, I hate using that word, explanatory variable, an explanation for the response. They should both go up or both go down together. Bottom of page 72, I see these sorts of patterns. A strongly positive relationship. Not only as I increase in X, do I increase in Y, as I decrease in X, I decrease in Y, but they're fairly tightly clustered together. The further apart they are, the more spread there is vertically around that line I'm thinking of, the weaker this relationship gets. All the way over there on the right, it appears that there's no real pattern going on at all. There doesn't appear to be a relationship. Although weak, positive, and no pattern, those don't look all that different, do they? I mean, okay, wait a minute. There's a little more down here that isn't here. There's a little more up here that isn't here. So maybe these are kind of bundled a little bit tighter. The same thing occurs in the negative direction. The one we were just looking at was a negative correlation. So I see something like these. A strong negative where they're tightly clustered, and a weak negative. But it's possible to have patterns that just aren't lines. And that last one, that's a parabolic sort of pattern, a curve. I have all sorts of patterns. I'm hoping to find, quote, simple patterns. And when I work with linear patterns, I can do even more. I could ask, where's the line? Algebra question. If I ask you for the equation of a line, what are you going to give me?
1 is mx plus b.
And what do those letters represent?
And then the slope, and b is like my intercept at 1.
A slope. A line with a positive slope, a line with a negative slope. I get the positive and negative correlation I get going on now. I could ask, what's the best slope to describe the cluster that's going on here? Now, there is a large amount of algebra that goes into finding the best slope. And the way you define best can change the way your line looks. So you might ask, what's the line that's nearest to all the points? Well, that would be the same as asking, what is the smallest gap between the lines and the points? Finding the smallest something, that's a calculus idea. I'm not going to do the calculus. What I am going to do is ask Excel. Can you show me what's going on here? What are the trends? If you right click on this data size, you see how the individual data have those frame around them right now because I clicked on one of them? The little white-ish bits around the circle. If I right click on the data value, gives me a bunch of options. One of those options says format data series. I'm going to scroll down, format data series. I can do all sorts of things here. I can change the shape, the size, the color, lots of things. But one of the other things I can do, right above that, says add trend line. It will draw for me a line. The line that is quote unquote closest to these data values. This line of best fit has all sorts of options over there. Remember I said we could find other kinds of relationships that weren't straight lines? Please look over there on the right. Exponential, linear, logarithmic, power, polynomial, floating average, moving average. There are all sorts of things I can do that will give me other pictures if I believe the data isn't in a straight line relationship. But for the moment, we're only looking for straight lines. Leah, you had a question?
So like you could like display the R squared, you just overlay snap.
Hold that thought. Right down here, it says display equation. If I click that little checkbox, boink, there's an equation. Now this equation tells me the slope of this line. Negative 120.19x. These down here are in dollars, right? So $1.25, 99 cents. If I could multiply those by 100 and get these in pennies, but these are in dollars at the moment. Slope. Slope is rise over run, yes? The fact that it's negative means it's a fall as I run. For every dollar of increase, my number of units sold should go down by 120. I don't expect to raise the prices $1 anytime soon, but I can now say if I'm going to raise it half a dollar, sales should go down by 60, half as much. If I raise it 25 cents, it should go down by 30, a quarter as much. I can now extrapolate. How good a fit is this? Well, that's the R squared value. We'll talk more about what that means, but in general, the closer that number is to 1, the stronger the fit. The closer it is to 0, the weaker the fit. Does that make sense? All of that can be found here, and if you grab this box, highlight that, you can change the font size to make it bigger so it's easier to read. Move it out of the way of the actual data so you can see it better. By the way, R squared value of 0.6 ain't bad. It's not a terribly strong fit, but it's not terribly weak. Quite often we're interested not in that number, but its square root. We're interested in R itself. What's the square root of that number? This is where you take out your phone or your calculator and calculate a square root form.
Like about 77.45%.
Oh, is it 0.77?
I took it at 0.6 rounded up.
Okay. So about 0.77-ish. Again, closer to 1. Oh, wait a minute. We took a square root, but this number should be negative. So I want the negative. Remember, when you take a square root, you get a positive value and a negative value. So I need to know which way it's going. Well, that's going negative. So it should be negative 0.77. That, again, that the closer it is to 1, the better I am. that R value is always between -1 and 1. Turns out, this is actually related to a cosine of an angle. And cosines are always between -1 and 1. If you want to know more about that, wait a while. We'll talk about it a little bit more in chapter 12. I'll be glad to talk to you about it in more detail because I thought it was a really cool idea. That these are actually cosines. Questions? Working with scatter plots works well for bivariate data. I'm only looking at price and units sold, and I said we might want to take temperature into account as well, right? I was thinking about temperature as a third variable here. I need to try and draw this in 3 dimensions. I can't do that in Excel. I can do that in other pieces of software. I can do things in Power BI or in Jamovi that give me images in 3D. I can do this same sort of idea with more data, but I'm probably best off looking at them 2 at a time to get these sorts of visuals. That's just easy. Lines in 3D are hard. We're not going to do it. Questions? If we have lots of different explanation variables and only one response, like the only thing I'm really concerned about is did I sell more or less water? But I say some of that could be by price and some of that could be by temperature. Then I can think of 2 variables I have control over and the response. Well, then I can look at them one at a time, or I can look at them all together, and we talk about how much variation each one has. This process with 2 variables is called simple regression. More variables, multiple regression, still works. It's just ugly. Questions? You'll do a lot more multiple regressions in quant business analysis, decision making BU 451 with Dr. Burns next semester. I must tell you that for the longest time, I just called all of these bar charts. I was informed that's not correct. This is a column chart. This is a bar chart. Big deal. One's horizontal, one's vertical. Columns are vertical, that makes sense to me. On the other hand, this particular column chart pisses me off to no end. See if you can figure out why this particular column chart pisses me off. Leo?
I think it's because there's a lot of different points there, different years, there's a lot of different times, and maybe it could be like not, maybe harder to get an accurate sense of all the sports there's 4 than like 2.
There are 4 different years involved here. According to this, it was every 2 years, so it's 14, 16, 18, and 20. Well, that's old data by now. It's asking about Instagram use. How often do you check Instagram? And the categories are several times a day, once a day, a few times a week, less often. Let's start right there. Less often. That less than once a week, less than a few times a week, less than once a few times a week, is on the right. And several times a day is on the left. Wouldn't you think if you check it more, it should be to the right and less should be to the left? Now, in the grand scheme of things, does it matter? Yes. Does it look like people are using Instagram less or more based on the trend in these columns? That's the problem. I can't tell, can I? And here's the second part that pisses me off. Look at the order of the four colors. Which one's on the left? Which one's on the right?
It'd be the newest one on the left instead of the oldest one.
They've done the entire time setup and the levels setup ass backwards, in my opinion. So this says several times a day. And my brain goes, oh, fewer people are checking Instagram several times a day, but this is the oldest data. This is the newest data. This says several times a day is increasing in use. But you can't tell that from this, can you? Deceptive practice. Being ethical with the way you draw your charts is important. Bars are preferred when labels are long because then they don't jam up under all the bars, under the columns. Unless you want to do something like angle them. You could write angularly under here. I'm not sure that's a worthwhile maneuver, but you see it done here on page 77. Hey, wait a minute. This looks familiar. What's that thing? We gave it a name. That was when it was cumulative frequency, right? As it even says right over here, cumulative percent. That's the graph of our cumulative frequency. We called it an ogive. And I said I was never going to use that word again. But we gave it a name, and it's our cumulative frequency. We've changed the order of the columns here because they're qualitative columns, not quantitative columns. In a histogram, we had a quantitative column. I couldn't rearrange the order, but these are qualitative. By putting the largest columns furthest to the left, this is called a Pareto chart. Italian economist Vilfredo Pareto in the early 1900s said, in particular with qualitative data. Remember, this is looking at concession stand complaints, right? And the biggest complaint of the concession stand is the food is cold. The other place you will often hear the Pareto name is something called the Pareto principle. Any of your business faculty talked to you about the Pareto principle before? It's also called the 80-20 rule. 80% of the issues come from 20% of the problems. The first two problems get me to about 65% here. 30, 50, all right, by the time I get to this third problem, I've got well over 80%, right? It's 3 out of 9. It's a low percentage. The larger proportion of the issues come from a small number of issues. You'll hear teachers talk about it. 90% of the class is great. Those 10% are killing me because they're the ones that are the problems. No. That's the same idea here. A few things are the majority of our problems. If you were going to fix something in this concession stand, I'd say there are 3 things you should work on first. You should work on the temperature of the food. You should work on the number of registers so people spend less time in line. And then maybe a vegetarian choice, because those are your top 3 problems. And you'd take care of a whole lot of complaints, wouldn't you? So, a rearranged qualitative histogram, a Pareto chart, allows me to focus on the few vital pieces in my terms of issues. Questions? The cumulative frequency here is not required for a Pareto chart, but I think it's very helpful for one. We also often see categorical data combined into time series. So here, let's look at med school applications. Med school applications in 5-year blocks. What we've done here is combined total annual applications with a gender differential. Rather than 2 side-by-side bars, one for men, one for women, columns, we've stacked those columns together. So overall, I can say applications are going up overall. I have to read the numbers to answer, are they going up for men and women? They're going up for one or the other? This is awkward to me. Stacked column charts don't give you a common reference. Here, the 2 sizes are right about the same. But here they've shifted. And here they've shifted further. What happened here?
On 15, men increased while women were at a lower pace.
Okay, wait a second. You've got those colors reversed. The red is the men's applications. The blue is the women's applications.
Yeah, I was talking about 2010 to 20.
Oh, 2010. So from here to here.
Yeah, women went at a slower pace than men.
Absolutely. But what happened between here and here?
Men decreased while women increased a lot more.
Can you tell just by looking at those 2 bars which one's bigger and which one's smaller when they're not referencing at the same place? I notice that the men's bar went down in size until I read the numbers. So a stacked column chart's another way I can put some information in the foreground and other information in the background. Hey, men's application to med schools went down. Women's application to med schools went up between 15 and 20. But yes, between 2010 and 15, men went at a faster pace than women, right? We have an increase here of 4,000, an increase here of 3,000. But that lack of a common baseline, again, can add or subtract useful information. Whereas a side-by-side set of columns seems to display to me more information. Questions? Pie charts, right? Do you know that this was the first color item to ever appear in a newspaper? A pie chart? The newspaper forever has been a black and white production. It's an old joke. What's black and white and red all over? The newspaper. Spell red, R-E-A-D. But what's black and white and red all over? A penguin falling downstairs. Ouch. USA Today was the first newspaper to produce color copies. They emphasized that by making the banner of the paper blue and putting in the bottom right corner of the front page their pictofact of the day. A survey question relevant to a news article further inside. The very first one was a pie chart. I get it, but you really have to be careful labeling all these different pieces. And you can see that while these are visually appealing, they can be far less practical than some other equivalent charts. That's the exact same data laid out in a rectangle. Again, the relative area is the expression of size. a 3D version can be made. But again, I'm going to see issues as I start to create larger and larger pieces, more and more pieces of smaller and smaller size. And then the comparison becomes an issue. Do those two wedges look like they're the same size? Yet they are. They're both 10%. As soon as you make that dimensional effect, that 3D tilt, the size becomes an issue. We'll see that in a couple of other places. Question? I love pictures. Pictures do a lot for me. But I am going to guarantee that you will spend far more time working in Excel on things that aren't pictures. Which one is my table? 23? Here it is. This data is about home sales. Notice I have lots of different options here. You should have seen this in the Intro to Business Software and Excel course. What did I build over here? Say it louder. Pivot table. The best thing about a pivot table, you decide what are the columns, what are the rows, what are the data pieces you're looking at. An average, a sum, a count. So in this particular table, I have ranch, and it says sum of square feet down there in the value. So I've got rows by subdivision, columns by type, and values are a sum. I can change that. If I right click on this, field settings, do I want a count, an average, the largest, the smallest, all sorts of things I can do here. The reason we work with pivot tables. What is the biggest reason to work with pivot tables?
You can make it one.
Well, if I work hard enough at the pictures, I can make most of the pictures how I want to. But yes, I can make these how I want, but even more.
I was gonna say like summarizing like large data.
Especially the larger the database gets. I mean, this is only 25 houses sold. If I looked at the past, I know 1,000 houses sold. This could be a lot more complicated. But there's an even better reason. Leo, you have one?
If you want to make the number formatting away, if you.
I can absolutely set that number up however I want. So in this second something, it says average of, and if I go to these fields here, I see this value thing change to be average, and I can set the precision. I can get 2 decimal places, 1 decimal place, however many I want. But what if there's a mistake in my table? Over here in my data set, what if there's a mistake? Pivot tables are live. If this house number 12, was not 3,200 feet, but was actually 3,400 feet, I can change that right here. And when I hit enter, tables automatically adjust too. I can also go into the pivot table and say, pivot table analysis. There's a refresh button up here somewhere, right there, refresh, boom. See how things changed? Look at these numbers here. Middle table, colonial, because I'm changing a colonial house, right? I changed it from 32 to 34. All of those numbers change. This is a live queryable database, like a SQL database. Somebody makes a change on the end, I run the report, I run the table again. and it generates a new setup. I am fond of pivot tables. I tend to use them less frequently because I'm a very visual person. But when presenting to a board of my fellow faculty members, actual numerical values may or may not help them. Having a pivot table, oh, well, we want to look at something different? Let me adjust this right here on the fly, refresh the table. Let's see what goes on. I could add rows to my home sales. If I insert them in the middle, I could go from 25 to 30 to 40 if I copied other data in, and then the pivot table would adjust automatically. Questions? I said this the other day. Mark Twain. There are three kinds of lies. Lies, damn lies, and statistics. The other quote of his is, figures never lie, but liars can figure. If I present to you a graph, I can lie my ass off just by the way I present the picture. Are cell phone calls increasing or decreasing in length? It's great data, isn't it? Looks like there's a huge difference between cell phone calls in 2015 and cell phone calls in 2020, right? It's a big difference. Is it really? Look at the y-axis of this graph. What do you notice? Going up by 0.2s, and it doesn't start at 0. It starts at 2.1. If I actually make this start at 0, it's a huge difference in cell phone calls, right? No. This exaggerates the difference because it stretches out what I want to see. I mentioned this book before. I'm not sure if I mentioned it in this class. There's a book by a guy by the name of Darrell Huff in 1954 called How to Lie with Statistics. A PDF copy of this book is on our Canvas page, I believe. Huff was actually working for the tobacco industry, trying to say that cigarettes were safe. So there's the data he was trying to present. And it took over 50 years to undo that lie. I can stretch my data. How many people have mobile phone service? What do they pay for it? What are you paying for basic mobile phone service dollars per month? Oh, it's not going up that bad, is it? Same axes, different scale. Same data. Which of these shows a more dramatic increase in price?
They don't want the right.
I would think so, right? That line's a lot steeper than that one. All I did was change the scale. I didn't do anything to the numbers or the dots. I just pulled the side of the picture over. Med school applications, right? We talked about med school applications a couple moments ago. I hate this picture. The white hot passion of 1,000 suns. First of all, why is it 3D? Why are these columns tilted and twisted towards us in some fashion? That means the stuff that's here is going to look bigger than the stuff that's back there because of perspective, right? And what's more, I have these two other pictures over here. Do they help? So why the hell are they there? To keep you from noticing a little of a difference there really is. Same data, same information, change in perspective. It looks like there's a really big difference between these two bars. There's actually no difference between those two bars. Angles change perspective. Remember what I was talking about, pie charts? Yeah. Can you tell what's going on here? I can't even tell you which color is the yellow. Is this one gastroenterology or is that urology? Which of these three different pinkish red colors is neurosurgery? This is the biggest one. What color is that?
Like a red.
But is that this red? Or is that this red? Or is it that red? First of all, I'm going to say this and it's going to be a very gendered stereotype. I can't tell anywhere near the spread of colors that my wife can. But this is true almost universally, that women see far more distinction in colors than men do. I guess it might be because of fashion. Is that about pink, rose, coral? What color is this stuff? I don't know anymore. My wife used to work at a yarn shop. I have never seen so many shades of blue in my entire life. Again, it's 3D. I can't even tell if those back wedges are supposed to be bigger or smaller than these side wedges over here. They've screwed me up. Images. What if instead of using columns, I use an image? And in order to keep the aspect ratio right, when I make it taller, I have to make it wider. I doubled from here to here. I got twice as tall, but I also got twice as wide. And that means the area of this box is 4 times the area of this box. And so it looks like an even bigger impact than if I just do them as uniform columns. I need to make sure I have good sources. Where did this data come from? Well, this one happened to tell me. Did this one? Nope. So where's it coming from? If I'm estimating something, I need to make sure I mention this is an estimate. If I'm rounding, especially with percentages, if I round, I might add up to more than 100%. I cannot tell you the number of graphs I have that add up to like 99% or 102% because they've rounded off the categories. Graphs and charts need to be presented honestly. It is easy to make the pictures, the numbers, say what you want. So now I want to just say, that's nice, I'm glad we have pictures. Let's look at some actual numbers. I want to start calculating things and finish with our chapter 3 on visuals. Normally, that would mean your homework is due to 2 class periods from now, right? That's Friday. Who's got the schedule? What's it say about Friday? Friday, February 6th. There's no class. There is a Middle States math competition going on Friday over in Sicilian Hall. I'm working that. So if you all want to come see the middle schoolers do math, come on down to Sicilian Hall. We'll be running from 9 to 1 on Friday. Otherwise, that makes this assignment due on Monday. We'll see you all then. I will see you Wednesday. We'll start our actual calculations.